Hi, I'm Renzhong. I'm going to introduce our work, Causality-Based Visual Analysis of Questionnaire Responses. Questionnaires are a handy tool for gathering information. For instance, psychologists employ questionnaires to assess the mental state of patients. Marketers aim to comprehend the needs of users. Education analysis are interested in examining students' habits. Causal reasoning is crucial for analyzing the data collected through questionnaires. Psychologists can understand that mood affects sleep, ultimately impacting one's health condition. Marketers can discover that advertising and product design collectively influence sales. Education analysis can also explore which factors are the causes of academic performances. Recognizing the significance of causality, relation researchers have put forth various methods to aid in causal analysis. Some work contribute to the empirical studies of visual causality. For instance, researchers have tested the efficiency of different visual channels for encoding causality and examined the expressiveness of different types of relation for presenting the causality. These works provide guidelines for the design of our system. Another set of works concentrates on designing interactive systems. For instance, novel layouts have been proposed to enhance the scalability of causal analysis. Causal reasoning has also been utilized for model interpretation. However, its works primarily focus on relatively small tabular datasets, typically containing fewer than 30 factors and are often inefficient for analyzing real-world questionnaires. To increase the scalability of causal analysis, we designed a system named Questionnaire Explorer. Users can explore the question combinations with potential inner causality and interactively explore the causal subgraph of each combination. The main challenge we encountered while developing this system is that important and valuable questionnaires often tend to be large-scale. These questionnaires typically contain dozens or even hundreds of questions. The causal graphs generated by automatical causal algorithm can become excessively large, making it difficult for users to analyze and interact with them. In the process of addressing this challenge, we summarized data needs from experts and proposed an analysis pipeline based on subgraphs to address the scalability challenge of causality analysis. We further built a visual analysis system and evaluate the system on data sets from different domains. Next, I will introduce the three parts one by one. To collect the data needs on causal reasoning of questionnaire data, we invited three domain experts and conducted two semi-structured interviews to collect their data needs. Finally, we derived 7 data needs across 3 major requirements. The first requirement is related to correlations. In the process of questionnaire analysis, causal analysis always starts from analyzing correlations. Users tend to explore causal relationships within combinations with questions that exhibit higher correlation. Therefore, automatically discovering some associated combinations is the first step in the analysis. Users may not be able to directly understand the relevance of automatically discovered question combinations. We need to provide explanations for each combination to assist users in determining whether the relevance truly exists. Lastly, in large-scale questionnaires, there are numerous question combinations. We need to provide interactive sorting methods to assist users in finding their preferred starting points for exploration. The second need is related to causal discovery. Manually constructing causal relationships between questions is a complex task. Considering that causal mining algorithm has become relatively mature, it will be more efficient to allow users to analyze and validate the automatically generated causal graph directly. During the analysis and validation process, users may need to correct errors in the automatically generated causal graph. We need to design interactive methods that allow users to express their specific needs directly. The last need is support for free exploration. The questions contain a wealth of valuable information that users can freely explore. First, they can engage in exploration at the level of question combination to discover relationships between different combinations. Additionally, users can engage in exploration at the level of respondents to discover connections and the difference between different respondent groups. Firstly, to explore the correlations between questions, we have devised a process based on the classical a priori algorithm to mine the most highly correlated questions in the questionnaire. The algorithm begins by traversing all question combinations in a top-down manner. Next, for each combination, the algorithm checks whether respondents' answers to these questions tend to concentrate on specific combinations of options. We use this degree of concentration to filter out relevant question combinations and then rank and expand the associated question combinations. After obtaining some relevant question combinations, the next step is to analyzing the causal relationships between the questions. There are several algorithms available to solve the causal graph. However, causal graphs with hundreds of nodes are often too large for users to analyze directly. Therefore, we partition the causal graph into smaller subgroups that are easier to analyze. To achieve this, we can use the previous mined relevant combination to guide the partitioning process. For example, consider a questionnaire with only 4 questions. We have discovered that question 1 and question 3 are highly correlated. Instead of presenting the entire causal graph of the 4 questions solved by the causal algorithm, we will utilize the VIS algorithm to identify the smallest subgraph containing question 1 and question 3 for user analysis. In this subgraph, question 4 will be omitted. Based on this idea, we have developed QE, where users can explore relevant question combinations, examine the causal relationships between question combinations, and understand associations and causality based on the distribution of respondent options. Users can also incorporate their prior knowledge by adding constraints. Additionally, users have the option to select a subset of respondents to init new explorations specifically tailored to them. Considering the large number of automatically mined question combinations, we use the algorithm to first automatically cluster the questions. Each cluster represents a group of related questions. Then within each cluster, we utilize upside to visualize the relevant question combinations. We display the question combinations using collecting lines to indicate their relationships. Now let's take a look at the causal wheel. We have taken inspiration from Causality-Based. Similar to its approach, we use pie chart to display the correlation of option distributions and use line thicknesses to represent uncertainty. To better align with the usage habits of questionnaire analysis, we have added linear regression coefficients and fitnesses to assist them in accessing causality. In the final wheel, we utilize a glyph based on pie charts to display the questions within the combination and the distribution of the respondents' options for each question. For example, the red sectors represent a group of individuals who have grades of A and good study habits. Analysis can gain insights into the characteristics and the distribution of these respondents. They can also click on the specific group to restart the entire analysis process, focusing specifically on this group of individuals. These designs constitute the QE system. We conduct user scenarios and user studies to evaluate the system. The studies are based on 2 datasets. The first dataset is about the education analysis. Our data includes 1,010 young people, and the target is to identify the reason for their happiness. The second case is about the employee engagement. We use a dataset with 475 employees, and the target is to find reasons for the choice of workplace. Now we will demonstrate the findings in the employee engagement cases. In the analysis of the employee engagement dataset, it smoothly navigates through our predefined process and identifies 3 core factors influencing employees' choice of workplace: proximity to family, spend less money on commute and food, and productivity. The linear fit achieved 0.23. Furthermore, during the free exploration process, users discovered other interesting insights. For example, managers tend to prioritize the sense of freedom over financial and efficiency consideration when choosing their workplace, preferring to work from home. On the other hand, developers, possible due to their younger age and lesser focus on family, lean towards working in the office because they enjoy the company's environment. In the user study, we aim to test whether our analysis workflow could assist users in exploring causal relationships in large datasets. To compare our system performance with the leading visual analysis tool for large datasets, Causality-Based, we invited 12 participants to analyze the 2 datasets mentioned earlier using both systems. In terms of average time taken to identify a cause, Questionnaire Explorer outperformed the Causality Explorer significantly. Additionally, Questionnaire Explorer demonstrated higher usability scores than Causality Explorer on several metrics. In summary, our contributions include proposing a pipeline, developing Questionnaire Explorer, and conducting an evaluation. Moving forward, we plan to enhance the scalability of the system by optimizing glyph design. Additionally, we will consider incorporating other aspects of questionnaire analysis, such as questionnaire design and data cleaning, into our system. We thank the funding agencies for their general support. Thank you for your listening. I'm happy to take any questions.